Okay, double integrals in polar coordinates. We are continuing on, and you had a few problems to work on, I think 5 for today. And so you're familiar with polar coordinates, how to set up integrals. You know, dA is equal to r dr d theta. But I think it would be good to do a few more problems with you. So let me give you a moment to copy this example down. Okay, so in this problem, we want to find the volume of a solid that lies above this cone. And you know, that cone, if we were to square both sides, we would get z squared equals x squared plus y squared. And you know from section 9.6 in, hold on here, in section 9.6 in your ebook, in your textbook, you had a table, table 2, that showed different surfaces, and the cone had an equation. Well, what I'm trying to say is, if you look at the equation of the cone in that table, this equation would meet the conditions of that equation. Of course, what we're doing is we're taking this cone equation and we're taking the square root of both sides, and we only have the plus part here. If we take z squared, if we square both sides, you know, of this equation here, we would get z equals plus or minus the square root of x squared plus y squared. But we only have here for the cone the plus part. So this cone is just the top portion of the cone. Okay, it doesn't include the, you know, the bottom portion of the cone. And so think about this. We have this cone, and we want to find the volume of the solid above the cone, but below this sphere. Below this sphere. So what would be, well, I mean, we have to think about how to start this problem. Okay, we have to think about how are we going to start this problem? Let me ask you this. Let me ask you this. Of course, of course, um, okay, let's see. Well, I want that really in black. I want it in black. Hold on. We'll get it eventually. So all of these problems in chapter 12, where you're doing double integrals, you have to find, your region D. You have to find your region D. What is the region going to look like? Because the region D determines your limits of integration. So how do you think we would find that region D? We have a cone. We have a sphere. We want to find the volume of the solid above the cone and below the sphere. Okay, so, here's a cone, and there's a sphere that's should above it, and Christopher said something I like. Okay, Christopher said something I like. Find the intersection. Find the intersection between the cone and the sphere, and that's absolutely right. So that is set them, well, why don't we take this cone and that Z and substitute it in if at where the cone intersects the sphere, the equation for the cone and the equation for the sphere have to be true at the same time. So Z would have to equal square root of x squared plus y squared. Let's substitute that in, okay, in the equation of the sphere. So that's what we're going to do. So in our solution, well, that's right. That's right. Christopher makes a very good point. Where the sphere and the cone intersect, the points of intersection, the Z coordinates for the sphere and the cone would have to be the same. So yeah, they share the Z. And that's why we can take, for that sphere, take the Z value and substitute in the square root of x squared plus y squared, which is the Z, which is what the Z equals for the cone. Are there any? And then, of course, we're going to do some simplification, and we'll get x squared plus y squared equals a half. And that's going to be a circle of radius 1 over square root of 2 centered at the origin. That's going to be your region D. So let me give you a moment to copy and think up to this part. And please let me know if you have any questions. I'll pause for a moment. Okay, so now in this case, the volume, to get the volume, we're actually going to have to take the difference of two volumes. One moment, let me hold on here. Just let that ring. Thank you. Okay. Sorry about that, class. The phone just rang. So, okay. So what we have to do is we have to take the difference of two volumes. So at the bottom here, at the bottom in these pictures that I've drawn, the volume we're looking for is the volume of this ice cream cone. Okay? Because that would be the volume above the cone and below the sphere. You know, here's the, be a little bit careful here. You know, here's the cone. So we got the shaded volume above the cone, but then the cone is bounded. Hold on. The cone is bounded by this sphere, above. So, I mean, the sphere, you know, the sphere keeps going, right? But we don't care about this part of the sphere, right? We don't care about that part of the sphere. We just care about the shaded area, the shaded volume, sorry. So in order to get this volume, we have to take the difference of two volumes. The first volume here is the volume underneath the sphere, over the circle given by x squared plus y squared less than or equal than a half. Okay, so essentially this volume is the volume of, say, like a bullet, maybe. Looks like a bullet. Or a pill. Looks like the volume of a pill. And what we're going to do is we're going to cut out from that volume this volume here. And this volume here represents the volume underneath the cone, over the circle x squared plus y squared less than or equal to a half. You see the functions of x and y, okay, are the top surfaces. Those are the surfaces that are on top. And the volume's bounded above by those surfaces. And that's what we have in each of these two pictures here. Okay, and so if you take the volume of the bullet to the left and subtract the volume of what's on the right there, I don't know quite how to describe that volume. It's you know, this volume here on the right. I'm not quite sure how to describe it. I mean, I have a picture of it. I'm not sure what kind of looks like that. But it's clear if you take the difference of those two volumes, you're going to get the volume of the ice cream cone. So, are there any questions on this problem? You have to let me know if you're uncomfortable. If you have any questions, you have to please let me know. Who's feeling good? Who's feeling good? Okay, Ryan's good. Both Ryans are good, and Eric. Christopher, similar to the homework. Well, yes, and this is, and you know, class, that's why I like to have homework due more frequently, so that then you're better prepared for new material. Okay, new kinds of problems. Very good. All right, thank you, everybody. Thank you also, Eric, Christopher, and Eric. Okay, well then now what we have to do is evaluate this. We have to evaluate this whole thing. So let's go to the next page then, if there are no further questions. Now, right now, you notice I have, incidentally, I will mention this. You notice that I have a dA here. I have dAs. Okay, so I'm not committed to using Cartesian coordinates or polar coordinates. And for my regions of integration, all I've done is say that I'm integrating over a circle with radius 1 over square root of 2. That's all I'm doing. I'm being very general, because first thing I want to do is get this part right, and then I can proceed forward to computation. If this part's all not right, then whatever I compute's not going to be right. So okay, now we go to the next page, and because the region D is a circle, that tells me that perhaps polar coordinates would be worth using here. Okay, perhaps polar coordinates would be worth using. Okay, well, with polar coordinates, we know that r squared equals x squared plus y squared. And so, again, you know, my, let's see here, one moment. I want that in black, really, but it's okay. My region D, let me just try this for a moment, see if this will work. I don't know if it will. No, that won't work. Hold on. My region D is this circle. I used to have a high school teacher that basically could draw a perfect circle. She was so good at drawing her circles, you couldn't really tell them from a real circle, like drawn with a compass. Okay, I'm not quite there yet, but I'm working on it. But you know that's a circle. Circle centered at the origin, and the radius is 1 over square root of 2. Okay, that's my circle. This is the origin here. And this is my region D. So whenever you're dealing with a circle, the limits are easier to use for polar coordinates, usually, than Cartesian coordinates. So what I do is I say, okay, well, dA is going to be r dr d theta. And my r limits are going to go from 0 to 1 over root 2. And my angle theta is going to go from 0 to 2 pi. That will trace out this entire circle. And of course, my functions will become square root of 1 minus r squared, and then just r, because the square root of x squared plus y squared is the square root of r squared. I mean, you know, this is just the square root of r squared, right? And that just equals r. So, okay. Are there any questions up to this stage here? All right, well then let's go ahead and work through the integration. Okay, and so what I always like to do is iterate the integral, which I did on this step here. But then, so I'm separating the integral with respect to r. I'm separating it out. How many like using these little iterating symbols in their work? How many find those helpful? Okay, John does, and Ryan does, Christopher. Excellent, excellent. Okay, well, oh my goodness, look at what I've done here on this next step. It looks like this double integral I've written as the product of an integral with respect to r and an integral with respect to theta. That's kind of interesting, right? So why was I able to do that? Why was I able to do that here? I mean, it's like I've taken this inner integral here and I've pulled it out in front of the first of that integral, the integral with respect to theta, like I just pulled it out in front. Why was I able to do that? Well, there's no, okay, Ryan's right, there's no theta variable in this inner integral. That's true. And okay, so then why was I able to pull the integral out? Well, this inner integral is going to be equal to a what? It's going to equal some blank. I'll give you a hint here. Okay, Ryan, very good. Ryan's very good at Wheel of Fortune here, and math too. Yeah, this here in this inner integral here, this is just a constant. I mean, I haven't evaluated it yet, but it's a constant. It has to be. It's a single integral with respect to r, one variable, and the only variable in the function is r, and my limits are numbers. That's gonna be a constant, so I can bring it out front. I don't have to, you understand, but sometimes if you and it won't always work, right? If like one of these limits here in the integral were a function of theta, you couldn't do this. But in this case, I can. Are there any questions so far? Okay. Well, then let's go ahead. If we're good, let's go ahead and move to the next page. So I have two integrals to compute. Okay, so this is really now, this is a times, right? This is not a dot product. This is a times here. Okay, well, this is calculus 1 then, right? So the second integral, that's easy to do. The first integral, I have the integral of a difference. I'm going to write that as the difference of two integrals. Okay, and then for the r times the square root of 1 minus r squared, I'm gonna do a u substitution. Okay, so let me let you copy up to here, and please let me know if you have any questions. Okay, so now, of course, because we did a u substitution here for this first integral right here, the integral with respect to r becomes an integral with respect to u. And so that means the u limits also change. What are the new u limits? Well, u equals 1 minus r squared. So 0, the 0 limit would become 1 minus 0 squared, which is 1. And the 1 over root 2 limit on top would become 1 minus the quantity 1 over root 2 squared, and that's a half. So our u limits are going to be a half and 1. And so I get down to this part here. And of course, the other two integrals are easy to do. Okay. Well, we have the antiderivative here, theta, on that last integral. So I get down to here. All right. Are there any questions at all? Who's feeling good so far? Okay. Excellent. Excellent. Okay. Excellent. Excellent. Well, all right. So all that's left to do is to compute this little integral here. Okay. And the antiderivative of u to the half, you can get that. You know that. So I'll go to the next page, and the antiderivative of u to the half is 2/3 times u to the 3/2 power. Okay, so, all right, thank you. I'm glad that Jamal, Eric, and Ryan, and John, and Christopher are feeling excellent here. I always appreciate participation, and All right, well then let's keep rolling here. So now it's just a matter of computing, you know. Um, WebAssign always likes simplified radical form for their answers. Always prefers it. Okay, and I mean, I think really, I'm just going to let you copy this down. I don't think there's. I mean, the 1/2 to the 3/2 power can be written as a half to the half power. Let me just see here. The 1/2 to the 3/2 power can be written as a half to the half power raised to the third power, because when you raise to a power, you multiply the exponents, and 3 times a half is 3/2. And so that's going to give me then the square root of 1/2, because a half raised to the half power is the square root of 1/2. That's square root of 1/2 multiplied by itself 3 times. So I think, you know, WebAssign would probably like take this answer here, but I'm just trying to get it in simplified radical form. Just because WebAssign, well, just because, you know, I like my answers to be simple looking, and so that's what I'm doing here. So this here is the volume. And let me ask you this, because this sometimes happens on these kind of problems. What if your answer were equal to 2 pi? I mean, let's say your exam 3, which will be posted later this week. Let's say you did a problem and you got as your answer 2 pi times the quantity 1/3 times the square root of 2 minus 1/3. Okay. Would you know that that answer's wrong? Could you tell? I mean, this is the wrong answer, but could you tell it was the wrong answer? You know, without WebAssign telling you it was the wrong answer. How could you tell that answer isn't right? Good. That's correct, Brian. This here is negative because 1/3 times the square root of 2 minus 1/3 is going to be negative. The first fraction is smaller than the second fraction. And in this case, you're computing a volume. So you know that can't be right. And that's one way to sort of help you, you know, check your answers, right? Are there any questions on that? Okay. All right. If you wanted to be, be even a little cleaner about it, you could write the final answer like this. Because here you could factor out 1/3. You could factor out 1/3 here, and that would give you 1 minus 1 over root 2. Okay, and so, so that's the volume of this ice cream cone figure. And, in terms of, economics, if this were like, the volume of an ice cream cone that a company's selling, don't you think they'd want to know the very exact volume as opposed to an approximation? If you approximate the volume and you're, off a little bit, well, then, when you compute the cost to make the ice cream cone is dependent on the volume of ice cream used. So if you're off on the amount of ice cream you use, even if your approximation is off just a little bit, if you take, a million ice cream cones, that could end up to be a fair amount of money. Okay. So, all right. Are there any questions before we move on? Okay. Well, let's go to, by the way, how many found having these pictures was helpful in thinking about the problem? How many found that to be helpful? Good. Visuals help. Yeah, and that's what, so you see, when you start on the problem, some students tend to get wrapped up in finding the limits of integration. Okay, and they right away, when they write down their, their double integral, they want to put limits of integration right away. But it's sometimes it can be a hindrance. You first want to make sure you kind of want to. This step here is very, very helpful because you know what you're trying to find, and then you can get the limits in a little later. So, okay, well, very good. Yes, Christopher. Christopher says it was very hard on the homework to visualize until I graphed it. Absolutely, and that's another reason why I wanted to reinforce this problem. Very good. Well, let's keep going here. Let's keep going. Let's look at another problem. Okay, find an expression for this iterated integral using polar coordinates. Let me give you a moment to copy the example down. Okay, so in this problem, we want to find an expression for this iterated integral using polar coordinates. Okay, so is it clear? And again, I always like to put my iteration symbols in. Is it clear that if we were to integrate, well, hold on here. Maybe I'll put it in red. This inner integral with respect to y, is it clear that if we were to try to integrate that inner integral with respect to y, it would be difficult? I mean, offhand, do we know, I mean, we're holding the x constant in the inner integral, but do we know the antiderivative of that square root of x squared plus y squared offhand? I mean, is there an antiderivative? No. So you see that these problems, the reason they want you to use polar coordinates is because in these problems, you're not going to be able to get a explicit answer using Cartesian coordinates. But with polar coordinates, it's going to be helpful. So let me ask you, what do we need to do first to you know, for this problem? What do we need to do first? What do we need to identify based on these limits? Based on these limits that are given here. What do we need to identify? So of course now, you know, the homework, you should all be doing it the right way, right? And that's, you know, not using a computer to get answers, but to do it, you know, by hand, like I'm showing you here. Come on, what do we have to find here? What do we have to find? If we're going to use polar coordinates, okay, we're going to have to set up a new double integral, right? In order to determine the new limits. Okay, well, certainly, Christopher, you're right. We gotta get x and y in terms of r, and we know that like the dA here is going to be r dr d theta. Certainly, that's true. But how am I going to find my limits? My limits with respect to r and my limits with respect to theta. How am I going to find those limits? Well, all right, Diodath, Diodath's thinking we're going to need to use a U substitution in the problem. Actually, it's going to be, well, you're right. You're actually right, Diodath. Later on, we will be doing that. But I'm not even, I mean, I got to get limits here. I got to get some limits. Whenever we do an integral, okay, whenever we compute a double integral, okay, this is the general form of a double integral. So we need to find the region D over which we're integrating, right? We have to find the region D. Okay, so in order to find the region D over which we're integrating, we have to be able, based on the limits that we have, well, I want to be a little careful how I say it. We have to be able to identify this region D based on the limits that we have. Okay, and what we're told in the problem here, I mean, well, let me go to the next page. So here, here's our solution. This here means y equals 0, right? Because the inner integral is with respect to y. This here means y equals square root of 2x minus x squared. So based on that, and then the x limits are going to go from x equals 0 to x equals 2, right? X equals 0 to x equals 2. So what does this look like? What does this look like? Well, all right, what I have to do is I have to take y equals the square root of 2x minus x squared and unwrap it. I don't know what that is exactly. I don't know what that function looks like exactly. Oh, I could graph it on my calculator and I would see it looks like a semicircle. But but we need a little more than that, right? So what I do is I square both sides, and then I bring over the 2x and the negative x squared. I bring those, I subtract and add those over to the left side. And then I'm going to complete the square. I'm going to complete the square so that then I can identify this function y equals the square root of 2x minus x squared. I can identify that as a circle. A circle centered at 1, 0 with radius 1. Are there any questions up to here? I'll talk about this part on the right then, but let me focus here because what I want to do now is I want to draw a picture. And actually my picture, there's an error in the picture. It's not a full circle. My region of integration I'm getting better at this. I'm getting better at erasing. Look at that. This is my region D of integration. This is the region D. So here on the bottom is the function y equals 0. That's what's on the bottom here of my region D. This is a D. And then what's this function on the top of my region D? What's that function on the top? That function is y equals, okay, what's the equation of the semicircle, Christopher? What should that equation be? And actually here, class, I should say a half circle, right? Because we squared that, it's a half circle. Right, so y equals the square root of what? Y equals plus the square root of what for this semicircle? Well, let's go to the double integral. Let's say we treated this region D as a type 1 region, which we'll do. Type 1 region, of course, means you go from bottom function to top function. Type 1. Bottom function is y equals 0. Yep. Oh, man. Hold on. So when the integral was with respect to when Cartesian coordinates, because we have a dy and a dx, okay, in that order, we're treating the region D as a type 1 region. The bottom function is y equals 0. That's that line segment on the bottom. The top function is y equals square root of 2x minus x squared. That's what the top function is. If you graph the square root of 2x minus x squared on your calculator, try it, class. Will you get that? Will you get this this semicircle centered at 1, 0? Try it. You get the semicircle? Let me know. Good, good. So you see this integral that you originally had, okay, this integral that you originally had here, okay, was again, you know, because you're doing dy dx, it corresponds to a type 1 region where the bottom function is y equals 0 and the top function is the square root of 2x minus x squared. And that's just going to be this doesn't include it's just the top here. That's going to be That's going to be what you see here. There's the semicircle on top, square root of 2x minus x squared, and then the line segment y equals 0 on the bottom. But we're going to convert our limits from using Cartesian coordinates to polar coordinates. That means then, that the circle here, I have to convert that, or I mean, it's a semicircle, you understand, but I got to convert it into a polar equation. And so what I got to do is where I have y, I got to write r times the sine of theta. Where I have x, I have to write r times the cosine of theta. And so, you know, I rewrite the equation in terms of r and theta, and then I add over the r squared cosine squared theta to the left side, sine squared, and I factor out an r squared. Sine squared plus cosine squared theta equals 1. So r squared equals 2r cosine theta, and so r equals 2 cosine theta. And so that's going to be an equation for the semicircle. And the radius, and then the double integral then would be equal to this double integral. The radius goes from 0. I mean, I drew a radius out from the origin, to the rim function, r equals 2 cosine theta. So radius goes from 0 to 2 cosine theta, and theta goes from 0 to 90 degrees. Okay, 0 to 90 degrees. Okay, so this would be when you're at 0 degrees, or 0 radians. And then this here is when you're at pi over 2 radians. Are there any questions on this? Any questions? All right, are we ready to move to the next page? So again, it's very important now, you know, these problems, that you practice these problems and practice them. You know, you got to practice. If you haven't, you know, if you don't get all the problems right, then use the late extension and get the practice in, because, you know, it's very important that you're, you know, walk into this exam feeling comfortable with the concepts. Okay, on that note, then let's go to the next page. We have a double integral to evaluate here. Okay, so I'm going to do my iteration. The inner integral is easy to do. All right, and that's going to get me down then to 8/3 times the integral from 0 to pi over 2 of cosine cubed theta d theta. Okay, so now that we're here, I guess I had my volume off for a moment. We're here, and what I'm going to do is I'm going to do the integration. Okay, and I get down here to 8/3 times the integral from 0 to the power of 2 of cosine cubed theta. And cosine cubed theta, I'm going to write as cosine squared theta times cosine of theta. But then I write cosine squared theta as 1 minus sine squared of theta. Now, why would I do that? You know, why would I do that? How can I compute? I must have done that for some reason. I mean, we know that sine squared theta plus cosine squared theta equals 1. And so cosine squared theta will equal 1 minus sine squared theta. No problem there. But why did I do that? How's that going to help me do the integral? Who can offer a suggestion here? Why would I do that? Okay, hold on. Good, John. Use substitution. That's exactly right. And what are we going to let u equal to, class? Sine of theta. That's right, Robin. You'll find, John, that letting u equal 1, well, John, I guess that would work too. Wait, hold on. I'd have to try it, John, your suggestion about letting u equal 1 minus sine squared theta. Oh, hold on. Wait, hold on. John is, well, I let u equal sine of theta. Let me show you why that worked. So I let u equal sine of theta. And the integral then becomes 8/3 times the integral from of 1 minus u squared du with limits 0 and 1. How do we get the 1? 1 is from the sine of pi over 2, because we're finding u limits now. And then 0 is from the sine of 0. So this u substitution is the one I work with, John. I'm not sure offhand, I'm not sure yours would work. Okay, you could try it, but I know this one works. I don't think it'll work because you're gonna, when you do du, if you let u equal 1 minus sine squared theta, when you do du, you're gonna get 2 sine theta cosine theta d theta, and you have an extra sign that you don't want. So I think you have to do it this way. But John will let me know if I'm wrong, right, John? Okay. All right, and take a moment to copy it down, the solution here. All right, are there any questions at all here? So we get 16/9. All right, I'll stop the recording then.